Welcome to Risk Roundup. As we witness an unprecedented convergence of technological advances in processing power, interconnectivity, cheap data storage, high fidelity rendering, physics simulation, natural language technologies, and so much more, it is important to understand what it means and why it matters. It matters because it allows us to embed individual intelligence in shareable concepts, and sharing, connecting, and integrating sources of knowledge, information, and intelligence is behind everything we humans have done in the past, are doing today, and will do in the coming tomorrow. When we look back at how knowledge and information sharing has evolved from those very first drawings and scribes, printing press and newspapers, libraries, radio to mass broadcasting, web search engines to ever increasing amount of data and digital content in so many different formats, it is remarkable to be witnessing a silent revolution that is moving towards data-driven insight, collective human intelligence, and collective machine intelligence. This silent revolution, the transformation of information sharing and intelligence gathering, the shift that we are witnessing from individual to social to technological through connected computers is leading us to a world where intelligent connected machines now play an increasingly dominant role as not only the creators and containers of collective machine intelligence, but also as human representatives that are capable of using that information on behalf of humans in so many different roles. These fundamental transformation changes humanity's relationship to knowledge, information, intelligence, and raises profound implications for the future of the human experience and endeavors. To discuss collective machine intelligence further, I am honored to welcome Lars Wood to Risk Roundup. Lars is the CEO of QAI Swarm and is based in the United States. He is also a visiting scientist at MIT, CIA, FBI, NSA, White House, and so many more organizations. His innovative career spans patented ANN algorithms, advanced microelectronics, thermonuclear and quantum physics, supercomputing machines, condensed matter physics, superconducting electronics, subatomic particle matter visualization, small molecule drug discovery where molecules use supramolecular forces to make decisions about their biological activity, and so much more. Welcome, Lars. We are honored to have you on Risk Roundup.
Thank you very much, Jashi. I am very honored to be here.
Wonderful, Lars. So let's begin our discussion by understanding knowledge sharing and connected computers. From the beginning of times, our early knowledge sharing relied on speech and other social behaviors. However, over the years, with advances in technology, now we have augmented this capacity for collective intelligence with writing, publishing, and now because of the connected computers, the computer code, in so many other digital formats. What role do you envision connected computers or machines playing in collective knowledge creation, sharing, and intelligence?
Well, first of all, what's necessary is that these computers have to have a common way of communicating. But it's not in terms of simple messages, TCP/IP or what have you. Those can be carriers, if you would, for the messages, but the messages themselves need to be of a kind of a language which they also can understand and interact with respect to artificial intelligence, let us say, and collective intelligence. So, for example, the reason that we are able to communicate and solve problems collectively as humans is because we have a common basis with respect to language. The languages have evolved for different peoples. For example, in India, obviously, I have a friend who's a Sikh, and they speak a different language than I speak. Okay, Chinese and so forth, Russian. But the basis of all languages is in terms of fundamental speech objects, phonemes, and so forth. And these are required for computers to be able to communicate with one another. I'm not saying that they have to speak like humans. I'm not saying that at all. What I'm saying is that the messaging that they do between one another has to be of a common base language, sort of a, if you would, a collective intelligence set of phonemes. And these would then form the basis for different types of languages with which they would communicate with. Without that, what you have is a bunch of machines that are whose complexity with respect to their interactions becomes overwhelming, because it's like, what API am I using and so forth. But with a common language that they can communicate with, and this is more of a signaling language than a language associated with verbal communication, that is really the breakthrough that is required for machines to actually have collective intelligence. Until that takes place, what you have are bits and pieces where you might have an intelligent capability or a machine here, IoT, that sort of thing, but they're all little black boxes. Without this ability to have common signaling, okay, that they understand, and it has to be a signaling which is, specific to artificial intelligence communication, okay? They will just be isolated and will not achieve the full self-organization potential.
No, that's excellent point that you made there, and you're right that communication and that language, that machines can interact with each other, not only just between machines but also between machines and humans. That is so very fundamental. And the human brain's unparalleled ability to design, modify, and build new forms of intelligence is so powerful. Now, in its so many different diverse forms, from human brain to computers of so many different sizes, from desktops to laptops to smartphones to now Internet of Things, machine learning, deep learning, intelligence is now becoming the most powerful and precious resource in existence. However, when we integrate this human intelligence with machine intelligence, then our relationship with everything on Earth and beyond in cyberspace, geospace, and space enhances, and it amplifies. So what potential do you see because of the convergence of imminent human intelligence with the machine intelligence?
That's a very good question. In fact, if you take from the perspective, and let's just call it common signaling as opposed to a language, okay? If there's a common signaling mechanism that all machines understand, where knowledge is passed and evolves and stored in terms of these common signaling terms, if you would, then what you have is a basis for translation into human interactions, because you can basically have a translator. And as a result of that, you have a collective intelligence which spans not just machine interactions with one another, with machine to machine, but in terms of human beings. Garry Kasparov, the chess master, said recently that when he was beaten by the IBM chess machine, a year later, everybody was beating the IBM chess machine with the addition of a small, simple chess-playing computer. So in other words, what was taking place was that these people that were not even as expert as he was, they were good, but not like him, were beating the now ruling chess master machine by just working with a machine that was much simpler, like a chess-playing machine, a chess-playing program at their side. That, I believe, is where things are going. The whole idea of a singularity, as the fellow, I'm having a moment here, but he basically is the person that built Stevie Wonder's, I actually met him, Stevie Wonder's keyboard many years ago. He had a company, he works for Google now. And he's the one who's been promoting this idea of the singularity in 20, 30 years. I believe what that's really going to look like is a combined singularity, if you would, where machines and humans together collectively have a new type of intelligence that work together. The reason I think this is because it's a lot simpler to do than having a machine which is omnipotent, if you would, or a computer that, with the algorithms doing all these types of things. It's a lot easier to have humans interacting with machines through a common signaling mechanism that enables the two together to work in a more powerful way. It's really more of an extension of what takes place now.
Yes.
It's a natural extension. Does that make sense?
Yes, yes, absolutely. You are right. And now we are at the brink of intelligence enhancement because of so many technological advances and so much new discovery in science and understanding that we have, which could be the most consequential technological development of our time and in history. So because of it, we will likely be able to frame artificial machine intelligence in terms of humanity's long history of building containers of collective intelligence. Do you hear an echo?
No, I don't.
Okay, sorry about that. So because of the computer code, connected computers and internet, it seems collective machine intelligence already exists. So many machines are connected all across nations, and because of that, the intelligence is already there. We just need to extract it now. What is the state of collective machine intelligence from your perspective?
Well, it's interesting. Right now, it's my observation is that people are focused more on the algorithms and basically building infrastructure. For example, the algorithms are old. However, with maybe linear types of refinements, but they are building infrastructure around those systems. Let me give you an example from microelectronics. Okay, so when people first started building machines using transistors, okay, it was very complicated and difficult to do. And the reason is because you only people who could do it were experts. You had to have a, PhD in solid state physics. It was very hard. I remember those days. I actually did that kind of thing for a while. But slowly, companies arose, like Mentor Graphics for one, which one of the early ones, that provided these infrastructures. Now, it took a lot longer then, all right, because the computers were the good computers were very expensive, like Sun Spark workstations and so forth. But these infrastructures and frameworks provided for accelerated development of solid state devices, and there were libraries and so forth that eventually arose. And so you could literally almost have somebody that didn't have much background in solid state physics, or none at all for that matter, be able to design complex circuits. Now, the corollary here is that's what's taking place today. The algorithms have been around for a while, but the infrastructure that's being built up, the platforms and so forth that are on the verge of being released, are key to enabling the basic use of artificial intelligence in a friendly fashion. So you don't have to be somebody that programs in assembly language to be able to create a program. You can buy Visual Studio and understand C++ or Java or some other language and be able to do it. That's much easier than coding at a very low level. The same thing is true here. The algorithms that are out there, what Google's using, IBM, they're all handcrafted. And what's taking place is an evolution in these infrastructural systems. Once that takes place, okay, people will start to focus on collective intelligence. Myself, I sort of look at things from the perspective of what do I not have to do, from my perspective. In other words, what do I, Lars, not have to work on if somebody else is going to do it? And so I see this taking place already, where people are building up these architectures that enable development of these AI systems very, very quickly. And so what I focused on, which I think is the next step after that, is the actual signaling between these systems so that they can communicate in a very fluid fashion. It's like in the old days with Microsoft or other software companies, and everybody had their own operating system, and they were all, and this was back in the days of DOS, and there was Unix and so forth, and there was AT&T's version of Unix, and it was very relatively complex for them to talk to each other. Now that's not the case. Computers, if a computer operating system can't talk to another computer operating system, it doesn't survive. So that problem has effectively been solved. In only a very short period of time, too. If you think about when Bill Gates started doing what he did to now, I mean, basically, it's completely different. The same is going to be true for collective intelligence. In other words, these systems that are similar to like companies like Microsoft and so forth, building their platforms will start to emerge rapidly now that the proof of principles using the faster machines, such as Google with their Go implementation and so forth, and IBM with Watson. Lessons learned, of course, Watson did great at Jeopardy, not so great at life sciences, simply because the problem is not so narrow. So what you'll see are these narrow applications developing in platforms as they are, and then making it easier with respect to the infrastructure, and then finally the common signaling. That is fundamental. That will result in a punctuated equilibrium. In other words, where things are going along for a while, and the systems are getting better and better, but then there's a big jump that takes place suddenly when these things can communicate in a common way that allows them to take advantage of each other's capabilities. Does that make sense?
Yes, and you're right that when it comes to machines, it seems currently we are at the state of algorithmic symbol manipulation. Right. And just the beginning. There is so much more that we still have to achieve. But do you think machines could take the words, emotions, actions, patterns, trends, and convert them into a meaningful language and communication? And the signaling that you're talking about that describes what they mean, do you think we'll be able to achieve that?
Yes, but you have to look at the machine learning algorithms differently. I'll give you a very quick example. Right now, most of these algorithms are focused on big data analytics and so forth. Even the Go program was actually doing that. If you think about it, trying to discover or search for a move that was appropriate out of a very large set of moves, but still finite. The big difference here is that they are basically pattern recognition systems. They are trained in whatever, or they learn in whatever mechanism they are exposed to, unsupervised learning, supervised learning, what have you. But they're basically doing pattern recognition. Deep networks take that a little bit, so it's like modular software, where you have modules that break down a complex problem so it can be learned more easily. Okay, it's like different regions of the brain, obviously a different substrate, but nonetheless, the same thing where you have different modules in the brain that are responsible for storing different types of information and then integrating those up so what you see is your consciousness. Now, the way that emotions are implemented is completely different. If you think about a process, let's say you have a mechanical process, okay, and you learn that mechanical process, and let us say that it's a simple cart that's moving, and this is a very old problem, by the way, a cart that's moving back and forth on a track. Now, the learning of that is not novel anymore, but the key thing is measuring the process. So effectively, there is stress associated with the learning process. Okay, in other words, these algorithms, it may be more or less difficult for an algorithm to be able to learn some problem. That can be measured. For example, the Bellman error is a very good example of an algorithm which has been around for a long time, but when applied to machine learning, can be used to characterize the stress associated with a learning process. If you take those stress outputs, okay, which also can include the velocity of learning and the acceleration, how acceleration of the learning process, that can be translated into a measure of emotional stress. Okay, if you think of emotions as basically dealing with a stress situation at the level of the acute stress response, that is, say, fight or flight. Okay, what you're dealing with is effectively chemical signals in the brain which are relaying the difficulty associated with solving some problem. Okay, so if you transduce that, if you would, to algorithms, you can measure the activity of an algorithm in terms of a machine learning algorithm, and derive from that metrics which basically provide for stress indicators, which basically provide emotions. And I've done experiments where I've actually been able to reproduce post-traumatic stress disorder in a single neuron, and also the feeling of epiphany, where without any training, just exposing a set of values to an algorithm and measuring these outputs, as I've specifically the Bellman era, okay, which has been around for a long time. You were able to have a measure of stress or a measure of insight. Something has taken place. In other words, the learning algorithm has suddenly started to converge. By measuring how the algorithms behave themselves and having those outputs, what you have is the basis for emotions in computers.
Yes, no, that makes sense. And also the advances in the brain technology, brain waves and brain-computer interface, that will also probably be very useful as we try to go forward with how to understand the emotions, how to understand what we are thinking, what the human thoughts are, and how we can decode all that using the brain-computer interface. So in the coming years, it's going to be very exciting what kind of developments we can have because of the advances in brainwaves and brain-computer interface. Now, incredible advances in natural language processing technologies have come about as a result of big data that has enabled powerful search engines and automated language translation and cloud-based speech recognition. Now, these advances in natural language processing impacts our everyday lives, irrespective of whether we are at home or at work. So what role do you see natural language processing playing as we strive for collective machine intelligence?
I think that in terms of collective machine intelligence, the natural language processing is a kind of signaling to humans that machines would do. I mean, so the machines, in other words, have as a translator, so the machine can communicate with the human being in a form, not just in terms of speech or written language, but also in terms of being able to see emotion, in other words, look at somebody's face and determine if they're happy, sad, and so forth. The problem is that, and there are fundamental challenges that have not been addressed yet. And these relate to, in fact, with Watson, the IBM Watson, where it did great on Jeopardy, which is basically they learned the Wikipedia is what they did. But when they went to a problem that was less focused, it doesn't work so well. And in the same sense, natural language processing, the really difficult part of that is context of use. I've defined 4 categories of machine learning, and being able to understand context of use. In other words, if you say a sentence which is ambiguous, but if somebody is if a human being is listening to that sentence and they look at the context of what you're saying happens to be, okay. So, for example, if I said "look out," all right. That could be because a piece of paper is falling or a train's coming towards you. You follow what I'm saying? The idea is that it's very important for these natural language systems to understand context of use. Without that, okay, they will be brittle. In other words, they will make mistakes and do things which basically some people call it common sense reasoning. Doug Lynette, for example, has spent his whole career trying to do that. So there are some fundamental challenges with respect to things like image understanding, not image recognition, but image understanding, speech understanding, and that relates to natural language processing that need to be solved or at least accepted that this is a limitation and to compensate for it in some fashion. In other words, you're not just going to say we can't do this, so we're going to all go home. Okay, basically you have to understand the issue that's there, which has been known about for 30, 40 years. Okay, and realize that no matter how much horsepower you have in your computer, it's not that kind of a problem. It's an exponential problem, and so you can't solve it using normal methods. Okay, so in terms of natural language processing, I think it's a huge part of the collective intelligence problem. But the issue associated with what I would call Category 4 reasoning. Okay, Category 3 reasoning is like playing chess. Okay, that's Category 3 reasoning. Category 4 reasoning is a big jump. It's Go. The game Go is Category 4 reasoning. Now you might think, oh my gosh, Google actually did that. Well, they actually didn't. They actually use brute force. They use Monte Carlo methods to actually identify the move. So they use neural networks and deep learning to identify the strategy that they wanted to use, but then they use brute force computing to identify the actual move. What we have to do here is, for at least natural language processing, is to either figure out a way to deal with this problem of context of use in using a brute force approach. In other words, using a similar approach to what Google did, sort of figure out what's going on with the neural networks and so forth, and then drill down fast, excuse me, with brute force computing. That's also okay. There's not any rules associated with this. There's no rule that says you have to solve the problem just like the human brain does. Okay, but nonetheless, the problem is there. It needs to be addressed, and until it is, you're going to have people be frustrated, and they'll have these natural language processing systems that almost work really well, but do silly things it can't understand what things that a child can understand.
Yes, no, that makes sense. Now, you made an excellent point there. And when I think about how human intelligence has evolved over millions of years and the nature of problems that the human intelligence has handled has relied largely on the use of prior experience. However, as we are trying to enable machines to reason from past experience, it requires a very radical detour, and it changes the direction from the artificial intelligence field's focus on semantic representation of knowledge to episodic representations. Now, I'm not sure if that is the path we are going forward with. Are we designing collective machine intelligence systems to solve problems by being reminded of similar situations from the past? Because for us to do that, we will need a lot of data, historical data, and it will be very difficult for machines to collect all that data. So, are we going that path?
Yeah. Well, you think about it. There's the data in different forms is actually out there. For example, if you look at the protein database that Rutgers houses, and there's thousands and thousands. I think that 40,000 proteins whose structure has been solved. That's a very small number compared to what the pharmaceutical companies actually have in their databases. They have much larger, and they use it for proprietary means. Now, so I think the information is actually out there. There are two problems. Okay, one is the information has silos around them. In other words, as in the case of the protein database, that's only a small percentage of the molecules. Likewise, there's intelligence information, for example, associated with national security. Only very small amounts of that are available to the public. I worked on basically a project back in the late 80s for the National Security Agency, where they had decided that they wanted to have a network that would be transparent to us, or rather to say the public, but be able to be every place. The project was called Embroidery, and it's now there, and it's probably gone through several iterations, but effectively it's the same system. it's now the basis for all of their intelligence gathering, everything that they do. It's obviously very secure, but the idea is that it has the ability to interact with public networks, even though public networks can't see it. Okay, so the point being is that the technologies to do this have been around for a while. But there are human-imposed barriers to these stores of knowledge, if you would, that prevent interaction. Also, there's a lot of noise. In other words, so noise would be information on the internet which is untrue or inaccurate. One of the problems that Watson one of the premises that they originally had in terms of healthcare was they could read all these papers using natural language processing, but it turns out, as you well know from your life science background, that not every single paper that's written in the life sciences is of value. People write these things because it's like publish or perish. So the idea is that what you really have is only a very few number of papers that are really worth reading and understanding and gathering information from that. So the problem, again, was silo. The idea being that the computer scientists who had no background in very little background in life sciences, they never discovered drugs or anything like that. They don't understand the issues associated with, the FDA and why most drugs fail. And it has nothing to do with that they don't work. They all work when they go into, clinical trials. The problem is the therapeutic window, the toxicity window, and that's what washes most of them out. So the idea is that the knowledge is there. Okay, the knowledge is there. What needs to take place is these silos have to be opened up somehow, and then the second part of the problem is the signaling to join these things together. Those two things are key, because otherwise you have noisy data or noisy information and an inability to correlate across vast resources. So those are the two issues I see as rate limiting that need to be addressed. And that actually points to the risk group in terms of what you're doing relative to basically having a global perspective with respect to technology, but it also relates to everything else. Without that, you're going to have systems which are not optimal and maybe not even not necessarily not functional, but unreliable. That's the worst thing.
Very true. Now, you made an excellent point about the challenges that we face because of all the silos that we have all across nations. Now, if we define collective machine intelligence as groups of machines acting collectively in an intelligent manner all across nations, the meaning of individual, where individuals could be software agents, could be human, it could be individual humans or individual computers or individual IoTs, collectively may consist of so many different things, so many mixture of machines or machines and humans and machines and humans and IoT things. So if we look at all of that collectively, what goals do we currently have of the rise of collective machine intelligence? What are we trying to understand? What are we trying to understand when we are looking at collective machine intelligence from all across nations?
Well, again, it's in terms of a common signaling mechanism. Without that, it's very difficult to do this sort of thing. That's a step that needs to be taken, and that's the one that I'm working on, where you have a common signaling technology where there's a protocol, if you would, for communication that all machines can interact using. Now, this is not like a lower level protocol like TCP/IP, which is just carrying messages, and you can have whatever you want in the messages. It could be video, could be voice, even could be text or emails, what have you. This is something that's layered on top of that. It's layered on top. It's like a knowledge signaling language that allows for communication of knowledge. And sharing of knowledge in a fashion where it can be used. So I'll give you an example. This is a problem that I actually experimented with in the late 90s. Let's say you have a collective intelligence composed of a bunch of agents that exist on different computers across the network, and you have a say one node, say node A, needs to have access to a spreadsheet program, okay, but it doesn't exist there. It doesn't exist on the node where node A lives, and it doesn't know where it is, because let us say that it could be any place. So the way that I addressed this was to broadcast a signal using the signaling language that I was developed, this knowledge signaling language, whereby other agents across the network picked up the signal and said, it's here, okay, and was able to then take that application and encode it in the form of the signaling language and send it to the node, the agent that required it, where it then redeployed the application on that computer and actually used it, okay? So this goes well beyond remote procedure calls and other types of things like this where you're calling into something that you know about someplace. What we're talking about here is the ability for computers, whether it be IoT or what have you, to be able to, or SAT, it could be anything, okay, to be able to say, I need something, who has it, okay, or I have something, who needs it. That's very important, and you need to do it in such a fashion that you don't have a communication overload. I'll give you an example of this. Problem has actually been solved by the military, although during the Vietnam War, they had a problem, had exactly this problem. I have information, the pilots did in the aircraft. I have information, but I don't know who needs it, and I need information, but I don't know who has it. And so what the solution at that point in time was to have lots of radio channels, 80 of them. But the problem was nobody knew what radio channel to listen to or talk on so that everybody else would hear what was going on. And it resulted in lots of casualties. What happened during the 60s was they addressed that problem using something called the Joint Tactical Information Distribution Network. And what this thing did was basically localize information, self-organize the information based upon your proximity to somebody else. So in other words, if you're far away from somebody else, from a pilot perspective, you're probably not going to be affected by what's happening to them. But the closer they get to you, the more important that becomes. And so the way this appeared on the terminal in the aircraft, and this is still in use today, is that it was first actually used in combat during the first Gulf War by actually Saudi pilots flying F-15s. Is that you start to see on your terminal messages that are becoming more frequent associated with that thing that was far away. So by having, and so what you ended up having, although it was not explicitly intended to do this, although the architect, Eric Ellingson of that system, who I work with, basically told me that he realized that after the fact when they did it, that the ability for information itself to self-organize. In other words, so it's not sufficient for the agents to self-organize. The information itself has to self-organize. And so by having the agents having the ability to ask that question, I need something, who has it? And then that response taking place, and either that information is provided automatically, okay, or sent without resulting in, a situation where, as an example, in a radio station, if the radio person says, I'm going to give away free tickets to the Super Bowl, you have a giant congestion problem because everybody calls in at the same time, okay? That doesn't work. And so you can't just have a system where you're saying, I need something, and everybody in the world responds at the same time, because you can't tell what's important. It's like a Google search that turns up bad terms. So what you need to have is the information self-organized using a method which allows for limiting stuff coming in. Now, when you do that, of course, you're basically running the risk that you're leaving something out that might become important. But if you do it in such a fashion where the impulse response of that information becoming available is linear, that is to say, it changes in an analog fashion, so as it becomes more important, it becomes more and more visible to you, or more and more in your field of vision, then I think what you have is a basis for sharing of knowledge and collective intelligence that addresses the problem of, where is the information, how can I get a hold of it without creating a giant congestion problem.
Sure, and I think what you are telling is probably related to the lack of categorization that we see, in World Wide Web, because we have this immense database that is the World Wide Web, and they have one addressing system at the physical level, and where you can reach every piece of information by the address, like whatever address you type on the server and so on, but there is no universal system of categorization. So how to make this growing database of connected computers or machines categorize in a way that we can search better? Because at the end of the day, if we are trying to search, we cannot search by, on the basis of the website address or on the basis of just some, categories. We need to have proper categorization so that when you try to search something, we get meaningful search, that can happen. So do you see that we are making any efforts in that direction?
Yes, I think we are, because there's a lot of work going on with respect to natural language processing and attempting to solve, or at least address, the issue of context of use. So you should be able to say something like, where should I go to eat today? Actually, you probably can say that now, but it's something more complex, but very, very general. Okay, where's the safest place in my town to go eat, or something like that, and something that's ambiguous, and the system then being able to go into the databases that exist and determining that going to McDonald's is not in line with what you wanted to do. Okay, so I think that the categorization, that there's a lot of work being done to do that. Again, the problem is in terms of the siloed information, because the really good stuff, okay, is still held in private hands, and you can't get at it. It's just not available. So you end up making decisions which are not optimal. So it's important. And then there's noise. There's basically people who write whatever they want to write on the internet, and they can appear as having a great deal of knowledge. I mean, for example, all this stuff associated with white supremacism or what have you. Okay, the idea being that if you were just to read that stuff from the internet, okay, you'd have a very skewed outlook on what was the way the earth works if you were an alien reading that. Okay, so you need to have the ability to categorize and basically have if you would, a meta layer that basically allows for this is white supremacist stuff with respect to a probability score or ranking of 0.9, say. Okay, so it can't be just there's a tag that says this is someplace to eat. There has to be a combinatorics that takes place associated with probabilities to address the issue of the noisy information. So what you have is a response from the computer that doesn't say with a 0.9 probability I think this is taking place. It has to be, I'm fairly certain that this is the answer to your question. So the categorization that needs to take place, it needs to move well beyond what's there now in terms of tagging and so forth. It has to be, again, in terms of signaling, again, the signaling language, which includes the ability to do approximate reasoning. In other words, being able to make statements about things which are not necessarily black and white, and then being able to aggregate that information and present it in a fashion which is, not ambiguous, even though the question that was asked was ambiguous.
Yes, no, it makes sense. Now, all these technological advances that we see ongoing, they allow all these connected individuals from across nations to work together in new innovative ways, and it gives us an ability to solve so many complex problems facing humanity together. And blockchain technology allows nations the digital infrastructure on which the global systems can be built. do you see that the time is now ripe for many more such systems to benefit from collective intelligence? Because if we say, our effort, we are trying to understand global risk, we are trying to see what kind of collective risk intelligence we can gather so that we can take a step forward in bringing some meaningful change to the complex risk and challenges facing humanity. But do you see that we can now build the global systems using this collective, not only human intelligence but also collective machine intelligence?
Yes, and you bring up blockchain. That's a really good example because blockchain is not just about Bitcoins. You can put anything inside a blockchain, okay? And the knowledge doesn't get deleted. It's there forever, all right? So whatever's there is just there. There are some public blockchains. There are some vulnerabilities. So, for example, in the Bitcoin blockchain, for example, and I know because I've done a lot of work on Bitcoin and blockchain, and I'm actually we run a full node here in Montana, where I am. I'm in Columbia Falls, but basically it shows up as Kalispell on the map. But the point being is that the blockchain is a really good example of a very, very simple protocol, which allows you to use a peer-to-peer approach that is neutral to the application. So, for example, Napster, the music sharing technology that was shut down by Sony and all these other companies, was a peer-to-peer approach. But the problem was two things. First, it became a proprietary system, and second, what they were trying to share, they shouldn't have been sharing because lawsuits were filed. Blockchain isn't like that. Blockchain is being used for all kinds of things. In the blockchain of Bitcoin, there are viruses inactive, but there are viruses that people have just stuck in there because they do, okay? But the point being is that blockchain is a technology which has the ability to basically be a breakout technology with respect to knowledge sharing, because the knowledge never goes away. Anybody can have access to it. You can't destroy it because it's replicated. Storage is not an issue anymore. Okay, computer performance speed is because of fundamental physical limits, but storage is not an issue. Storage is getting cheaper and cheaper, so there's really no issue associated with blockchain technology and how big the database is. Networks are getting faster, so you can download the blockchain. I downloaded the entire blockchain of I think it was 185 gigabytes in 7 hours, something like that. Okay, so and I don't have and my connection is only 100 megabits per second. So the point being is that the blockchain technology is a perfect example for a breakout capability, which is not controlled by a company that everybody has access to. Governments will try to get control of this because it could potentially impact the entire internet itself in terms of how information is stored. So instead of having HTML pages and so forth stored in SQL databases, okay, which is what they do now, or Oracle databases or what have you, the same information can be inside a blockchain and much more easily accessible. Okay, and the reason blockchain is so important is because it's open source, okay, and it's self-organizing. That's really important, meaning that it doesn't require somebody to be turning a crank to basically make it work or have it function. So I think blockchain is an example of a technology which could be a breakout technology for breaking down the silos of information. The dark network obviously was sharing stuff, some of which shouldn't have been shared, but the point being is that the law enforcement is basically almost completely shut down dark network. Okay, it's almost gone. Basically, they raided the servers. They raided the servers, shut them down, so 70% of the traffic is gone. This has been documented on the internet. It was relatively easy to do. Blockchain, you can't do that. Okay, if somebody were to try to shut down blockchain, you just couldn't do it because the information is shared every place, and it's not something you can file a lawsuit against necessarily because it's not necessarily going to have all just your stuff in there. Okay, that belongs to you. So I think that blockchain is a really good example of a breakout technology that would combine with machine intelligence. You have the basis for breaking down these silos and effectively a new way of sharing information, which is redundant to failure. During the Cold War, we used to have this thing called multimedia. Okay, it wasn't what it's called today. Multimedia today is a different thing. Back then, multimedia was if a nuclear bomb drops on something, what other way can the message get to you? That was what multimedia was. Okay, blockchain is an example of multimedia in that context. You can't destroy it someplace. You'd have to take out the entire network in order to all the nodes in order to be able to make the blockchain fail. So that is a key technology for breaking down the barriers that are currently present with respect to these information silos in these different nations.
Absolutely. And the biggest, the most attractive attribute of blockchain technology is that it solves the trust problem, because it enables individuals and entities across nations, its government, industries, organizations, academia, all the components to transact with each other, as it removes each component's needs to trust the other. We don't need to, trust. So because we know that this will not be compromised, as you were, just explaining. So tools play a defining role when we design and define systems for collective intelligence, be it a risk management system or any other system that we are trying to, develop. So do you see a fundamental change in how we approach collective intelligence due to blockchain, or any system that we are trying to develop because of the blockchain?
I think that blockchain is critical to this. Now, the algorithm, if you read the original Nakamoto paper that was published in I think it was the early 90s, I might be wrong on that, but basically he goes through, it's not clear if it's a he or it's a they, but effectively there is an issue with blockchain, a technical problem. That basically relates to security, and it has to do with how hash codes are identified. And the idea is that as the blockchain grows, the probability of this vulnerability being exploited becomes less and less and less. So the more complicated the blockchain becomes, the lower the probability is that the vulnerability can be exploited. It has to do with how hash codes are calculated, which is the fundamental aspect of blockchain and the basis for blockchain mining. Some people make money doing that. There are companies that formed to do that. But notwithstanding that, blockchain is still a huge, and you have to think of blockchain as not the end all. It's the beginning of a way of doing things, which is peer-to-peer, that is self-secure, okay? Which doesn't delete any information, remembers everything, okay? That can be used as a foundation. I'll use that word, a foundation to build these intelligent collective systems that break down these barriers. Okay, I think that blockchain is a key technology, not just for currency, but for all kinds of documents, information sharing. I even was told a couple weeks ago that somebody is using blockchain in Florida to fly drones collectively. In other words, so the drones actually use the blockchain. I haven't looked into it, but the drones actually use blockchain to communicate common information amongst one another. So if they're doing it there, drones are a really good example, because drones lead the way for where collective intelligence is going. Okay, the swarming that they're actually deploying now, the military applications that they're using are important, because the types of problems that they need to address are the same general issues that we're talking about here in terms of enabling collective intelligence. So the fact that somebody's using blockchain, and it came from an extremely reliable source, who actually, his name was Peter Fingar. He's a consultant to top-level management at IBM and so forth, and an expert on technologies which have become basically breakout technologies. like for example, the cloud and so forth. He was one of the first to promote the cloud, and now AI and blockchain. He's the one that where I got this information on the blockchain. So the point being is that blockchain, I think, is a breakout technology. Both public and private blockchains are really no different, other than the fact that the firewall doesn't allow them to talk to each other. But if you had a signaling mechanism that enabled that, you basically have the basis for effectively a very, not infinite, but pretty big knowledge base that you could draw upon at will from any place, virtually instantaneously, because of the peer-to-peer sharing.
Yes, yes, of course. Now let's talk about your organization. It seems you have worked for decades at the crossroad of physics, life sciences, computer science, and military operations towards the objective of a sentient collective machine intelligence. Would you care to elaborate on where you are with reference to achieving your objective of sentient collective machine intelligence?
We're at the point where very soon, within months, we're going to release a platform that actually integrates all these different things that I think are important. It's about 300,000 lines of code and developed since 1995. And we've worked on different types of problems, security problems. My background in with the intelligence agencies and communication security and also encryption and those kinds of things, satellite communications, provided for a framework that for security, sort of a compartmentalization of the system. But that's basically integrating a known technology into how agents function. The system was applied for 13 years to small molecule drug discovery successfully, using the signaling protocol that I've alluded to. And I believe that, and the reason it's taken so long is two reasons. Number one, I did not want to be influenced by outside forces to the extent where it suddenly was diverted from the path where I wanted to go. And number two, you couldn't get there anyway without having moved into different spaces and become knowledgeable in those spaces. So fundamental to what I realized as an example was that, signaling, how molecules signal each other in proteins and so forth in living systems, that's pretty fundamental to how things should work. The key thing was figuring out a way to do that in a computer that made sense in terms of signaling. And I believe the version that we have, which has been tested on a number of very difficult problems successfully, has demonstrated that. Also, interestingly, it's a peer-to-peer system, just like blockchain. It works in the same exact fashion. It's composed of agents that talk to each other. It's composed of neurons which have virtual connections. So the idea of having something like this, and what we intend to do is release it as a platform. It's something that people, just like as if you were to buy, Microsoft Word, and basically, apply it, and it generates turnkey systems that just deploy. And either in terms of basically anything on Windows, any Microsoft platform, and it has proxies to work on other operating systems. So I think, for example, that I have come to a point where I'm satisfied with this collective intelligence, which I call quantum artificial intelligence. And there's a reason for that. I won't get into it right now, but there's a reason for that. It has to do with how the signaling works. And it's not doing quantum mechanical things. It's the signaling the signaling spreads like a wave function. So in other words, it's like you throw a pebble into a pool, and the wave that spreads is how the messages propagate throughout the system. But there's some differences with respect to how messages are received, which gives it this quantum viewpoint. But the key thing is that I believe that we're at a point where the system can be released, and we're just figuring out exactly how we want to do this. The main thing that we want to do is get it into as many hands as possible. That's the key thing, okay? So, and so other people can go beyond what we've done, and we spent a lot of money doing this, but, we've also made a lot of money applying it. So the point being is that to provide it to others, and open source is not necessarily outside of the idea of how we're considering to do this.
That's a good point, and I think that would be the right move. And perhaps a closing question for us to ponder is, how do these new kinds of collective machine intelligence systems that we are trying to build to solve all the complex challenges facing humanity, not just individual nation or individual business or individual government, but the humanity. So as we go forward on that, what it means to be an accountable human, that is something that we need to understand, and what role each one of us individually and collectively have to play in solving the complex challenges that is facing all of us here on the earth, and if we look in the cyberspace or if we are looking at the space. So I think, and I hope that this approach to thinking about collective machine intelligence can help us to understand not only what it means to be individual humans, but what it means for us as humans to be part of some broader collective humanity system. So having said that, what would you like to tell our global viewers and listeners, and especially the young minds all across nations who are trying to make a difference? Money is not the main motivator to a lot of young people across nations. They are all trying to solve big problems for the particular nation or for the global community. So what would you like to tell them?
I think, the most important thing is to communicate. That is the most important thing, to communicate and not be afraid to be, to ask any kind of question. Because the only, obviously bad question is the one that's not asked. So that is the single thing that I would say that, increased communication, because that leads to increased understanding. So people understand where somebody else is coming from. I'll give you an example. There's a lot of, in the United States, of course, this anti-fascist group that's a sort of a counter-response, a co-evolution, if you would, to the people that are fascists. Now, the thing is that the languages that are used are incorrect, because if you go back to when fascism actually arose, in terms of its large scale basis, it was in Italy. It wasn't Nazi Germany. Nazi Germany was basically a race based economy, but because they didn't have any problem with immigration or anything like that. Their problem was with people's race, okay, and that there was only certain races that could profit and other races were not allowed. Fascism is very different. So the point being is that people end up communicating and saying things. In fact, fascism is very close to certain forms of socialism. Keynes, the famous economist, basically said things that Mussolini thought were great, and Keynes was a extremely liberal economist. So the point being is that people need to communicate and understand, listen, because without that, you could basically be having your messages pass right by each other. And so the receiving end is not understanding exactly what the sending end is saying. So I think communication for the young people is the most important thing, because that resolves ambiguity, which can lead to resolving conflict.
Yes, now that's a good advice. Now it is said that none of us knows everything. You're right about it. None of us knows everything, but
Right.
we all know something. Individually, we all know something. So if the collective human intelligence and collective machine intelligence is the foundation of space age, we have to take advantage of that. Now, the capacity of nations, its government, industries, organizations, and academia, communities that we have to evolve towards higher order integration and performance through collaboration and innovation is a need of the time. So thank you, Lars, for participating in Risk Roundup today. We appreciate your thoughtful insight on collective machine intelligence, and our global viewers and listeners would benefit tremendously from the information you provided on collective machine intelligence, and especially the signaling efforts that you are working on currently and its benefits to the society and its future. So even if a single individual or entity can come up with an idea to explore collective machine intelligence to solve complex challenges facing humanity based on the understanding they receive from the discussion we had today, the Risk Roundup dialogue has been of service, and we thank you for that.
Thank you very much for having me.
Wonderful, Lars. So when we look back at how knowledge and information sharing has evolved over the centuries probably, and how this web search engines to ever increasing amounts of data and digital content in so many different formats today, it is remarkable to be witnessing a silent revolution towards collective machine intelligence. It is time to evaluate that we collectively evaluate the security risk of the silent revolution towards collective machine intelligence. Risk groups, cybersecurity, geosecurity, and space security risk research centers are created for this very reason, to identify, evaluate, and manage the risk facing NGIOA in CGS, that means nations, its government, industries, organizations, and academia in cyberspace, geospace, and space. We at Risk Group believe that risk management, security, and peace, they walk together hand in hand. Though security is related to management of threats and peace to the management of conflict, risk management is related to management of security vulnerabilities as well as management of conflict. It is not possible to conceive any one of the three without the existence of the other two. All three concepts feed into each other. We believe that the security we build for ourselves is precarious and uncertain until it is secure for everyone across nations. Tradition becomes our security, so if we build a culture of managing risk effectively, it will lead us to security, and security will lead us to peace. Let's manage the existing and emerging risks together. For more information on the Risk Roundups, to watch the Risk Roundup videos or hear the Risk Roundup podcast, please go to riskgroupllc.com and do not forget to subscribe and share. Until next time, I'm Jayashree Pandya, host of Risk Roundup, signing off. See you next time. Thank you.